All right, so what we're going to do is let's start this last portion. We'll go through the easier parts first, then we'll take a break, and then we'll end with the math. All right? All right. All right, so EM algorithm for latent variable models. We're now going from the specific case of Gaussian mixture models to the general case of latent variable model, which is kind of nice because things actually become easier. We're not writing down Gaussian densities because we are doing it in an abstract setting where we don't have any particular density we're using. So things get a little bit shorter, actually. OK. All right. So the abstraction of the Gaussian mixture model is going to be this latent variable model. And we're going to talk about two sets of random variables. Just like for Gaussian mixture model, we'll keep them the same letters, z and x. Z are the unobserved hidden variables. Previously, they were the cluster assignments. Now they're whatever. And x are observed variables. So the key is that x are observed, z are not observed, but z are involved in the overall distribution for our data. So the joint probability model, the set of possible joint probability distributions that we are considering on x and z, will be parameterized by some theta in some parameter space, capital theta. All right? So this theta in the Gaussian mixture model case would have absorbed all the pi's, all the mu's, and all the sigmas, which we'll now just write as theta. All right? So it's OK. All right. So suppose we have a little terminology. Suppose we have a data set dx1 through xn, and for simplicity, let's just write x for all the points we observed, x1 through xm. And we'll find that that's basically all we need to work with. And if z are the corresponding unobserved variables, z1 through zn, let's write z for the whole collection of them. All right. Now, so an observation of x, so all the x1 through xn, that's called the incomplete data set, whereas xz would be called the complete data set. In practice, we don't observe xz, but it's something that is helpful to work with. All right, so the learning problem. This is the maximum likelihood version of the learning problem. Given an incomplete data set, x, find the distribution, the density on D that gives the highest value. So we're searching for the parameter theta that gives the observed data x the highest density. All right, so that's the learning problem. And the inference problem we've spoken about is still the same. Assuming we know the parameter theta, given the xi that we observe, what is this distribution on the zi, the unobserved piece? All right. All right. OK. So yeah, the point I'm making here is that although for Gaussian mixture models, the learning is hard and the inference is easy, the inference is not always easy. That's a very nice aspect of Gaussian mixture models. There's entire courses talking about how to do inference in more complicated probability models. Often you'll find this in like a graphical models or Bayesian networks class. They're a big part of the problem. A lot of the discussion is more on the inference side of things. And for learning, they'll say, oh, just do EM algorithm. OK, so that's what we're doing. All right, so just a little going from the likelihood to the log likelihood, fine. There's this terminology. Sometimes P of x is called the marginal likelihood, because if xz is the joint likelihood, we're marginalizing out over z. We're summing or integrating out over z. If z is continuous, now z might be continuous, in which case this would be an integral. But let's stick with the discrete z case for now. It's simpler. All right. Pxy we'll call the joint or the joint distribution. The marginal log likelihood, log p of x, just a little terminology we'll be using. This is what we really want to optimize. We observe the data x. Maximum likelihood is, let's find the theta that maximizes that likelihood for what we observe. All right? But that's hard. It was hard in the Gaussian mixture model case. because of that sum blocking the log, remember? That's what made this hard in the Gaussian mixture model case. And in general, it's hard for latent variable models. But in the fully observed case, when we observed x and z, in Gaussian mixture models, it was very easy. We wrote it down together here. It's easy to do learning in the fully observed case. And this is something that we assume to be able to apply the EM algorithm. And in fact, we assume a little bit more, which is that we assume it's also easy in the kind of soft assignment case, that we have a distribution for z for given each x. OK. So here, we're going to write that as q of z. So for each latent variable, z, we're going to suppose we have a distribution on z. So that could be, for instance, the conditional distribution of z given x. All right? But we're being generic here and say, suppose someone just gave us a distribution for the z's. All right? We don't know exactly what z, but a distribution on them for the latent variables. Then can we compute the expected complete data log likelihood? All right? So let's study this for a moment. So here's our complete data log likelihood. That would be easy to maximize, we've assumed. And now we've introduced something new, which is we don't actually observe z, so we can't write this down. Because we don't know z, we can't just plug in z to that expression. But someone has given us a distribution on z, somehow or another, and how we'll come to later. So a guess about what the latent variables are. So if you have a guess, this distribution on z, we can consider the expectation of this conditional log likelihood with respect to the distribution on z. That's what's going on here. This is the expectation. We're basically saying, let's try every value of z. For any fixed value of z, this thing is easy to work with, p log pxz. And then we're going to take the weighted average based on this distribution over z. Right? So the idea is that if somehow we can manage to come up with a guess for z, then we can talk about maximizing the parameter, finding the parameter that maximizes the expectation of this full data log likelihood. All right. So to do EM algorithm, we're going to need two little math facts. The first is Jensen's inequality. Jensen's inequality talks about expectations of functions that are convex or concave, right? So the way I remember it, we can look at it in a second, but the way I remember it is this. Expectation of x squared and the square of the expectation of x. Which is bigger? What? Expectation of x squared is larger. How do I know that? Well, the variance of x is like expectation of x squared minus the square of expectation of x. You know the variance is always greater than 0. So the difference of these must be greater than, OK. This is how I remember the direction of Jensen's inequality. This is because the square is a convex function. It's true. So for any convex function, f, the same inequality holds, and that's called Jensen's inequality. So expectation of f of x is greater than or equal to f of the expectation of x. All right? If f is concave, the direction reverses. In our problem, we're going to have a concave function, logarithm. All right? That's the first thing. The second thing, have you guys encountered the KL divergence? Kullback-Leibler divergence? That is the second thing that we will need. So there's a lot one can say about Kullback-Leibler divergence. I'll just give you a light sense of it. In some sense, it's a measure of how different two probability mass functions or probability density functions are. So to get it out of the way, it's not a proper distance metric. It doesn't obey the triangle inequality. It's not symmetric. It's probably the most metric violating aspect. But Nevertheless, so we write it like this, KL divergence between P and Q. And it involves the probability mass functions of P and Q in this way. And you can see it's not obviously symmetric. In fact, it's not symmetric. But this is the definition of KL divergence. And a few key properties that we'll use are that this is basically all we need to know about the KL divergence, which is that it's non-negative. So whatever P and Q are, the KL divergence is non-negative, which is nice if it's even trying to measure some kind of divergence or difference between distributions. It's nice to be non-negative. It's equal if and only if the two distributions are equal. Excuse me. The KL divergence is 0 between two probability mass functions if and only if the mass functions are exactly equal. The same is true for densities in the continuous version of this. All right. So this fact will help us in understanding some properties of the EM algorithm, because we're going to come across an expression that we're going to recognize as a KL divergence. So we're going to be looking for something of this form, and we're going to say, oh, that's a KL divergence. So I know that this is non-negative, and I also know that if, for instance, Q is fixed and I want to maximize this or minimize this with respect to P, I need to make P equal to Q, these sorts of things. OK? Yes?
The two bars in the parentheses, are we drawing on some other math notation?
We might be. I don't know. And it's also just written as KL with a comma. Right. I don't know the history of that. Anyone else? No. All right. So the theorem that the KL is non-negative and 0 if and only if they're equal, that's called Gibbs inequality. It's a simple consequence of Jensen's inequality, which we just went over. I don't want to dwell on it, but it's a nice little exercise. All right. So just a quick rehash. Our goal today, our goal for the whole lecture is to find theta that maximizes this thing, log P of x given theta. Everything we're going to do is in service of that. And we went through this. We did this odd thing. We said, oh, let's suppose we have a distribution on Z. OK. Why? I don't know. And then with the distribution on Z, we can talk about the expectation of this joint log likelihood, and maybe that's easier to work with. And what seems a bit arbitrary is actually a very common tool. It's part of what's called a variational method. And it shows up a lot in probabilistic methods, in Bayesian methods. And so if this is the first time you're seeing it, it will seem surprising or unusual. But it comes up very often. So it will gradually become like a part of your toolbox. So the general thing that's going to happen here is we're looking to maximize this thing with respect to theta. We don't know how to do it directly. What we're going to do is we're going to come up with a lower bound on this function. This is a function of theta. We're going to come up with a new function of theta that's a lower bound on it. We're actually going to come up with a whole collection of lower bounds on this. Each will be a function of theta. And the EM algorithm, if I were to say it in a sentence, is basically we're trying to maximize this. We don't know how to do it. We're going to maximize our lower bounds as best we can. All right? So what we're going to write down now is our first lower bound on this thing on the left. And we're going to find a lower bound by introducing this new object out of the blue, which is a distribution on Z, the unknown variable. And for every distribution on Z, we're going to get a different lower bound on this marginal log likelihood. All right? Every lower bound will itself be a function of theta. And so for every Q, we get a different lower bound, a different function lower bound of theta. I'll just write it real quick. Suppose this is a parameter space theta. And what I'm drawing here is the log, this represents the log marginal likelihood, which is what we're trying to maximize. We don't know how to do it directly, and we're going to find a lot of lower bounds to this thing. So we're going to find a function like this. We're going to find a function like, like this. All right. I don't know what they're going to look like, but they're all going to, every single one of these is going to look like a function that lower bounds the one we actually want to maximize. And each one of these is going to be derived through some choice of a q, a distribution on z. So this might correspond to q1 of z. This would correspond to q2 of z, q3 of z. All right. So this is why this new object, this distribution on z, enters the picture. Because in a moment, we're going to show how for each q, each distribution q, we're going to be able to get a lower bound on this function. Is that kind of clear? Quick rehash. This green thing, this is a function of theta, the parameter. We're trying to maximize this likelihood function as a function of the parameter theta. OK. Great. So let's get a lower bound. Yeah, question?
These z's are still our latent variable z's from
Z's
the whole lecture.
are now and for always the latent variables. That's right. Right. OK. So, all right. So the first line is inequality. We're going to have a few equalities before we get our inequality. Marginal log likelihood. We can always write that in terms of the joint, x and z, and then sum out over the unknown thing, z. This is inequality. This is standard probability. Great. Let's break that up with the old multiply and divide by the same thing trick. All right? So we have an equality by multiplying and dividing by q of z to the previous line. All right? Now, sneakily, this distribution q has entered into the picture. All right. Now we have a logarithm of this weighted sum. Now qz is a distribution, a probability mass function. So this is an expectation, right? Because for every z, this is the probability of z times some function. You could think of this whole thing as a function of z. All right? So this is the probability of z and some function of z. We're summing out over z. That's an expectation of this thing, of this ratio, with respect to the distribution q. All right? So we have the log of an expectation of some function of z. What do we know?
Positive.
Say again?
Positive.
We have Jensen's inequality. Remember? So if Jensen's was for, so let's say f is concave now. So f of expectation of x, and then we have expectation of f of x, right? And there's an inequality here. You guys remember which way it goes?
For concave x, right?
F is concave. All right, I'll just. It's great, right? And the way I just worked that out in my head is I'm like, OK, well, if f were x squared, I know this thing better be larger than this. And f concave is the reverse. So, OK. So here we have the log is concave, of an expectation. So f is like the log. So this thing must be greater than or equal to what we get if we switch the log and put it all the way in front of this function. Yeah? All right, so we're going to get a greater than or equal to. Now this is the expectation of this logarithm of that function. All right? That's our lower bound. So we've chosen q, and we now have a lower bound. And we can think of this as a function of theta, right? We're trying to maximize over theta. So as a function of theta, this full expression is a lower bound on our likelihood. And we're going to denote this whole thing LQ theta. Q, because Q is what gave rise to this lower bound, and it's still a function of theta. Is that clear? Now this holds for every Q and theta. It's unrestricted choice of Q. So this is kind of, so for any fixed Q, this would be like LQ of theta. So I'll just write that. LQ1 theta, LQ2 theta. Okay. Is that clear? All right. Okay. Okay. And as I mentioned, this exact inequality, what we just worked out, you'll see this so many times. Every time you read a tutorial on some kind of variational method, this will be there. Yes?
Shouldn't we take the log of q of z also? Like q of z should be inside that log thing. Because we are just swapping the expectation and the function.
So you're asking, should the log be in here? And the answer is no. And the reason is that this sum and q, this together is the expectation. Okay? This is just like, if this were an integral, this would be in the d part. So the function we're taking the expectation of is in the big parentheses. But that's a good question. All right. So EM algorithm is maybe the most basic example of a variational method. All right. So there's a little bit more terminology. This is, I'm just taking this expression and rewriting it in one line, the inequality. So some more terminology. This thing on the left, it's the marginal log likelihood of the data. It's also, in some circles, it's called the evidence. More importantly, the more common term is that this lower bound is called the evidence lower bound. Evidence. Or ELBO, ELBO. You'll see ELBO a lot, ELBO, evidence lower bound. Right? And so EM algorithm is basically maximizing the ELBO over q, over theta and q, right? All right. That's more or less all there is to it. Now it's just a few details. Okay. Oops. Okay. So we've derived this. We have our form for the lower bound LQ theta, our ELBO. And just to kind of write in equations what I have said, whereas the maximum likelihood would be kind of find the theta that maximizes this log likelihood. In the EM algorithm, what we're going to do is maximize the ELBO over theta and q. So instead of this thing, which we can't quite get a handle on, we're replacing it with LQ theta, the lower bound. And now we want to maximize this over q and theta. We don't actually care about q, so we're not taking the argmax over q. We're just maximizing over q because we don't really care about it. But we're taking the argmax over theta for the maximum over q. Yeah? Bless you. Pause for comment. All right. OK. All right. So here's an illustration. It's kind of what I drew on the board. We're going to come back to this image a few times. So the red is our marginal log likelihood. We want to maximize this over the x-axis is theta, the unknown parameter. The blue curve and the green curve are two different lower bounds for different q's. All right? And we want to find, so the maximum of blue is not a great approximation for the maximum of red. The maximum of green is better. And if we find the maximum over all lower bounds, well, that might just be good enough. We might be able to say something about that. OK. So we're going to think about this as a coordinate ascent problem, just like we have coordinate descent, coordinate ascent, where we're going to alternate between maximizing q and maximizing theta. So at the highest level, the EM algorithm is choose some initial parameter theta. For the fixed theta, find the distribution that maximizes the lower bound. And then for that distribution, find the theta that maximizes it. All right? And repeat. So what we'll show is that what's basically easy to see, actually, from a picture is that the thetas we get have monotonically increasing likelihood. So doing this iteration, things are never going to get worse, basically. So how does this look pictorially? We're starting at some theta arbitrarily. All right. Now, at theta, we find the q that gives us the best lower bound. So at this point, the lower bound function that would be the best lower bound would be whatever is exactly tangent to the line we're trying to lower bound, right? So we're looking for a lower bound that is exactly tangent at the point theta old. Such a thing would be the best lower bound at that point. And it turns out we can find that q, and that will give us this entire function, the blue function. All right, so we first find the q, that's the best lower bound at that one point. Then we maximize this lower bound. So that would jump us from here to here. Theta nu maximizes the blue lower bound, right? And now we repeat. Now from here, from theta nu, we would find the best lower bound, which would be the green line. And then we maximize that, which would bring us to here, and so on. Is that clear? So we keep hopping from the maximum of one lower bound to the maximum of the next lower bound. Right? Sorry. We have a lower bound. We find the maximum. We hop to that point. We find the new best lower bound at that one point, and we hop to its maximum. All right. It's clear? So what we have is we basically have two subproblems we're going to have to solve. One is the argmax over q for the lower bound for fixed theta. And the other is the argmax over theta of the lower bound for fixed q. And it turns out we can solve each of these problems in closed form, which is what makes the EM algorithm so practical. There's just a little mathematical manipulation we want to do to make it kind of transparent how to solve these problems. So this is the lower bound that we had. Remember, this is from swapping the log by Jensen's and bringing it inside. Yep. All right. Let's break it up in a different way. So this is a joint of x and z. Let's factorize that into the marginal of x times z given x. It's fine. And now let's break that up using the fact that these products and ratios break up in a logarithm into sums. So we've taken the first kind of this factor and this factor and left that here, and then broke out the px given theta factor over here. Is that clear? Just log breaking up that this product of terms. And what do we see? What do we see? Now it's time to recognize the KL divergence. So this is like the negative KL divergence between the distribution q and the distribution of z given x and theta. All right? Just something one wants to recognize. This thing over here, what you notice here is that log px given theta is independent of z. So that comes out, and now we're left with the sum over z of a distribution. So that's just 1. All right? So this piece simplifies right here. Oh, what's this? That's something special to us today. Log px given theta.
So what was on the other side of the inequality?
Log px given theta is, it previously was on the left side of the equality. And the reason it was in the prominent top left position is because that's the topic of today. That's what we're trying to maximize. This is what we're trying to maximize over theta. This is the lower bound for any given q. And we have an equality, which means the gap between the thing we're trying to maximize and the lower bound is given exactly by this KL divergence expression. So I've rearranged. This is what we want to maximize. It's equal to, no inequality, equal to the lower bound on it plus this KL divergence, which precisely gives back the gap between the function and its lower bound at q, which I always find quite amazing. All right. So that's nice to see. And now let's put it back into the lower bound, with the lower bound on the left in the position, because now we're going to use this some facts we know about KL divergence to figure out how to maximize q. All right. So for fixed theta how do we maximize over Q? So we have this decomposition on the right. And note that there's no Q on the second term. So we only have to think about maximizing this first term. All right, we know very little about KL divergence, but what we know is sufficient. What can we do to maximize the right-hand side, in particular this KL divergence term?
Make it equal to the conditional probability of C on X and theta old.
Fantastic. So Q, we're trying to find Q to maximize this. If we set Q equal to this PZ given X theta old, what is the KL divergence? 0, because the KL divergence between equal distributions is 0. And is that the maximum that we can achieve for this function? It is, because KL divergence is always non-negative, but we're negating it, which means in this context, this term is always going to be 0 or smaller. We figured out how to make it 0. We're done. We just maximized it. So for a given theta old, the Q maximizing this distribution is exactly the P of Z given X theta old. P of Z given X theta, that is interpretable. In fact, we've seen it before. How would you think about that? In the Gaussian mixture model case, that was our soft assignment to clusters for a given X. All right. In this more general setting, it's just the conditional distribution of the unknown variable given what we've observed. So for any given parameter setting theta, the best distribution is this conditional distribution. All right. So that's our Q star for a given theta. And it's nice to draw a connection between the equations and that picture, which is that, so this is our green line, or our red line in the other picture. This is the likelihood we're trying to maximize. And when this is 0, we have an equality between the lower bound and the marginal log likelihood. So to be very clear, at theta old, so at a particular point on the theta axis, and for the right choice of Q star, these curves are exactly equal. And otherwise, we know always the case that the marginal log likelihood is lower bounded by our lower bound. So in particular, it's lower bounded at Q star for all theta. All right, so that gives us some support for drawing our picture like this, where the two curves are actually touching. So we didn't know before we just found it that the best lower bound at theta old was exactly touching the curve. We know that would be great, but what we have now shown is that, in fact, we can find a Q such that the lower bound is tangent to the curve at that point. All right. OK. That's all. Now the other direction. For a given Q, how do we maximize theta? All right. So we'll just write things down in a slightly different way. Here's, again, our original expression for the lower bound. Now let's break it up and bring this QZ and this QZ over here and leave the top part on the left. All right. So we're maximizing over theta for fixed Q. There is no theta here, so that part's irrelevant. This we saw early. This is the joint log likelihood, and we're taking the expectation with respect to this distribution Q over the unknown variable. We've talked about that before. That's called the expected data log likelihood, expected complete data log likelihood. All right, we want to maximize this piece with respect to theta. Well, that's exactly what we said better be easy to do if we're going to do EM algorithm. That was a bit of an assumption of the problem. So it turns out that this is easy to do for a Gaussian mixture model, and this is something that just needs to be easy to do for this to fly. All right, but so the takeaway here is that maximizing the lower bound for fixed Q over theta is equivalent to maximizing this expected complete data log likelihood for the given Q. All right, so we can summarize now. We start with the theta old. Then we have what's called the expectation step, where we find the best distribution Q star for the given theta, which we know how to do. It's that conditional distribution. And then in preparation for the next step, which is to fix Q and find the best theta, we write down this objective function. J of theta is, for this fixed Q, the lower bound. And expanding the definition of L, this is an expectation with respect to this distribution on Z of this term, this factor. So this is why it's called the expectation step. As we set up the objective function for the next step, which is where we're going to maximize this over theta for fixed Q, there's an expectation inherent in this objective function. So that's why it's called the expectation step. And the next step is called the maximization step, where we take this objective and we maximize over theta. All right. So find the best Q, expectation with respect to that Q, maximize with respect to theta, iterate. All right. That's basically it. The rest is just kind of getting comfortable with the fact that this is always improving your log likelihood as you move theta. And also one other thing. Does it mean anything special if we could find the global maximum of LQ theta to the lower bound? So the lower bound, as we vary Q over all possible distributions and theta over all possible values, does the maximum attained there, is there any gap between that and the maximum of the marginal log likelihood? That's the question that we'll address. All right. So I think it's clear that the likelihood monotonically increases because we only ever hop to the maximum of a function or to a new function that's tangent to the point at that point. So we only either go higher because we're maximizing a function or higher because we're jumping to a better lower bound at that point. So in every step, we're never going to decrease the likelihood. We're never going to find a theta that has a lower likelihood. All right. So it's just saying the same thing in some math. All right. But now is a very interesting point. Suppose we found somehow or another a global maximum of the lower bound, right? Q star, theta star. So what we do know is we know the form of Q star, right? We've proven that for any theta, Q star must have this form at a maximum, conditional distribution. And the claim, maybe surprising, certainly satisfying, is that theta star, corresponding to the maximum of the lower bound, is also a global maximum of the marginal log likelihood, which gives us really strong justification for trying to maximize this elbow, this lower bound. Right? So how does that work? So let's do the following. So this is just for any arbitrary theta, we know that the optimizing Q is of this form. Now, so what's the general strategy here? We're going to say pick any theta prime, show that the marginal log likelihood of your data under theta prime is less than or equal to the marginal log likelihood under the theta star, which optimizes the lower bound, right? So we're trying to show that theta star, which we got by optimizing the lower bound, is also the global maximum of the marginal log likelihood. We're going to do that by saying no matter what theta you choose, its marginal likelihood is always going to be less than the marginal likelihood for the theta star. Right? And this defines theta star maximizing this function. All right, and this is just a few steps. First, we have this exact equality, where the lower bound plus the KL divergence. Then we have the fact that for the chosen Q, this second piece is 0. Boom. And now, how do we get this inequality? Think in terms of definition of Q star theta star?
We define them to be the maximizer.
Q star theta star were defined to be the maximization over all values for L. So this would be true for any Q prime L prime. And then finally, we're back to this equation of this form, because we know that Q star must have, Q star is of this form, and so the KL divergence piece is 0, and so this is just equal to the marginal log likelihood. All right. Wow. So if we can find the global maximum of the L, we have found the global maximizer of the marginal log likelihood. Can we actually find the global maximizer of the elbow? Maybe, maybe not. We have a theorem. OK, so there's a bit of some conditions. So think of the algorithm, think of the EM algorithm as stepping you through parameter space, through theta space, and let theta n be where you are after each of those steps. And we have this transition function, m, which you can think of as mapping you from one theta estimate to the next one after running one round of EM. So m takes you from one theta to the next. And then assumption, the log likelihood function that we're trying to maximize is differentiable. And what's the best we can hope for? That we can end up at least at a stationary point, so a point where we can't locally improve our likelihood. So at least a local maximum is basically the best we can hope for this type of method. So if S is the set of all those points, stationary points, gradient 0. So here's the theorem. I feel like Vanna White. OK, under mild regularity conditions. So we could check the paper if you want to see those. Wherever we start, the limit of this algorithm is always going to be a stationary point. OK, that's comforting. 2, it's a fixed point of the EM algorithm. So if we end up getting there, we're going to stay there. And finally, very nicely, so we're not going to pause in our increase. All of the proofs we had so far were saying we never decrease. What we now have is that the likelihood strictly increases to this is no longer the global maximizer. Theta star is now just a stationary point, right? But we will strictly increase to that stationary point unless or until we hit it. And that's the content of the theorem. All right. This is not too old, 2005. Right. Questions, thoughts?
Pretty high level question on all the latent variable stuff. So we started out wanting to maximize over theta this log p of x. But we didn't know how to do that. And so then we cleverly introduced these latent variables z in this distribution Q.
One sec. The latent variables were always there.
Okay, that's kind of where
but we didn't really know how to marginalize out over. When we marginalized out over the z's, which were always there, we got an expression. The expression for this was not easy to maximize. That was like the gradient methods won't work well. That's where we have the sum blocking the log. Things don't simplify well. There's no closed form solution. So then we had this tactic, yeah.
I think then really I was going for like a concept check on like, was this all really a technique for maximizing this where we introduced the z's, or did we already decide in our problem that there is some latent variable doing some work that?
Yeah, okay, so right.
It sounds like it's the latter case.
Yeah, it's the latter. So we came to this problem and thought a latent variable model makes sense here.
Yeah, exactly.
I would like to use a latent variable. I'd like to fit a latent variable model where there's some unobserved z's, which could be cluster or whatever, and these x's that we observe. I want to do maximum likelihood. I can't find a closed form solution. Gradient descent reportedly doesn't work very well. This is another approach. We find these lower bounds. the elbow in the way described, and we optimize the lower bound. And by the theorem, that gives us a good chance of finding not necessarily the maximum likelihood, but a good proxy for the maximum likelihood.
Do we use gradient ascent to find the maximum for the L functions?
OK, great. Do we use gradient ascent to find the maximum of the L functions? Great question. That would come into a variation. So so let's go. Let's go back to the algorithm. OK. So basically, this piece. Here we've written an argmax. That's a maximization problem. How do we know that's easy? Well, EM algorithm will work when we can solve this. For Gaussian mixture model, this has a closed form solution. So it's very easy. But in general, we may need to do some kind of a gradient method to do this maximization problem. That's correct.
And is there like a stopping point that if we reach a stationary point, which is not the global maxima, do we stop there?
We will have no idea. We won't know how to detect whether we're at a global maximum or just a stationary point. At least I don't know how to.
So at a stationary point,
we're done. If you're at a stationary point, you're done. The best you can do is start with a new random initialization and run again. Yeah. Or I'll just say, any more questions? I'll just say like 3 more things. OK. Because this might help flesh out our understanding a little bit more. So variations on EM. So the EM basically had the 2 problems. This is the E step and the M step. And either one of these can be too hard to do in practice. In the Gaussian mixture model, they're both easy. They're both trivial. They're both closed form. Remember, OK. So for the M step, this is your question, we don't have to find the argmax. We can be satisfied with just finding some theta that improves over the previous theta for the given Q. So that would be called generalized EM, GEM. You can also do a gradient step, as you were suggesting. OK. Good. Now, the E step, that can also be difficult. How can that be difficult? Well, when we take the optimal Q, the Q star, the next thing is to compute this. We need to compute this expectation with respect to Q star of this log ratio. This expectation may not be easy to compute. It's easy for Gaussian mixture models, but in general, it may not be. And so what can we do? So this standard approach, which actually happens in most variational methods, it's not needed in EM. But in most variational methods, there's an additional thing that happens, which is that rather than finding the best Q star over all possible distributions, which we did, we restrict Q star to a subset of distributions. And we restrict it to a subset for which this expectation is easy to compute. All right? OK. So let me find us there. All right. So now we'll take Q star to be the argmin over some restricted subset Q of that KL divergence. All right. So that gives us a looser lower bound on our maximum on our marginal likelihood, but it allows us to proceed. If you can't take that expectation with respect to the best Q star, you're stuck. So we restrict to a simpler Q. Things like mean field approximation, if you've heard of these things, they are restrictions of the set of distributions you can consider. All right. Yeah, let's stop there. Yes, I'll take questions.
Is this similar to like earlier when we studied about conjugate functions?
Conjugate prior?
Yeah, so that they could integrate.
Oh, you mean restricting Q to some subset that makes it easy to find the expectation of? It is related in the general sense of choosing a restricted family of distributions that are easy to work with. I'll let it go that far. I'm not sure if it's a deeper connection, though.
Yeah. So when we say if the best Q star is not easy to work with, how do we know what the best Q star is? Do we like?
No, so the Q star, go ahead, sorry.
So do we try different distributions and see where we are getting a higher?
No, we know that we can search over all possible distributions, and we know what the best is. I can tell you right now. The best Q, this is a restricted search over just, but if we search over all distributions, the best Q will be PZ given X, theta old. So the only issue is that PZ given X, theta old may be difficult to use in the next step, which is taking an expectation with respect to that distribution.
Does that mean this sacrifice the convergence? The final solution you get doesn't mean it's the global.
Yeah, so our theorem no longer applies. Yeah, that's right. I don't know what more you can say.